Hi everyone. You should today during science you should be following along on your Google form. There's a couple questions, but if you're listening, it's going to be super easy. All right. How does light as a form of energy cause matter to change? What do you notice when you move from a shady area into the sunlight? How does the sunlight feel on your skin? You may feel your skin warming. If you spend a lot of time in the sunlight, you may also notice your skin feeling hot or even burning. Have you ever hung clothes in the sunlight to dry? You may have noticed that objects dry faster in the sunlight than they do in the shade. Sunlight can cause all of these changes because light is a form of energy. Remember, energy is a force that causes something to change, anything to change. But what exactly is light? In order to learn more about it and how it behaves, you must first know what it is. Light is a form of energy that can be seen. As you learn more about light, keep in mind that it is a visible form of energy that travels in waves. Remember that energy is the ability to cause change. We know that light is a form of energy because of the changes it can cause. For example, solar panels can transform light energy from the sun into electricity to power our homes. Energy also can transform from one form of energy to another form of energy. We observe that light energy transforms to thermal energy when objects warm up in the sunlight. We feel thermal energy as heat. Other forms of energy can be transformed into light energy. For example, think about the electric lights you use every day. Light energy does not travel through the wires to the lamp. Electrical energy travels through wires to a lamp. Once the electrical energy gets to the light bulb, it transforms into light energy. So that's kind of hard to think about. When you turn a light on, the light energy is not what travels through the wires. The electricity, which is a form of energy, travels through the wires, and then when it gets to the light bulb, it transforms into light energy that we can see.
Light is a very important part of our everyday lives, and it is the focus of this real-world science program. What is light? When you think about light, what comes to mind? Light bulbs? Fire? The sun? Well, those are all sources of light, but do you know what light is? Simply put, light is energy that you can see. On a sunny day, not only can you see light, but you can feel the heat it gives off too.
All right, electric lights, the sun, and fire are familiar sources of light, but how can we define light itself? So we know now that light is an energy that you can see. How do wave properties of light explain how it travels? Light travels in the form of electromagnetic waves. We cannot see an electromagnetic wave in the same way that we can see a water wave or a wave on a rope, but it acts in a similar way. There are different types of electromagnetic waves. The light we can see is called visible light. Each color has a different wavelength. You can think of a wavelength as a distance from the top or the crest of one wave to the crest of the next wave. There are types of light that human eyes cannot see. These include radio waves, microwaves, infrared waves, ultraviolet rays, X-rays, and gamma rays. Each type has a different wavelength. So remember, when they're talking about wavelengths, they're talking about a squiggly line, kind of like this. Those are wavelengths. So when they're closer together or further apart, that tells what kind of wavelength it is. So a light wavelength is something you can see, and each color has a different type of wavelength, which means that the little squiggles are further apart or closer together. We can also describe electromagnetic waves by their frequency, which is the number of waves that pass through a point each second. Each second. Waves with shorter wavelengths have higher frequencies. All right, so we just read that wavelengths look different when they're different colors. So when we look at a rainbow, we see all of the colors of the visible spectrum. The visible spectrum, visible means being able to see, and a spectrum is like a spread out different things, kind of. The visible spectrum is just a small part of the electromagnetic spectrum. The electromagnetic spectrum is composed of electromagnetic waves of a broad range of wavelengths and frequencies. So remember, that means different squiggles of wavelengths are different squiggles, and frequencies, which are how many squiggles there are. The wavelengths of the light we can see range from 400 to 700 billionths of a meter. So you can see we're talking about something that's really small. So we know that a meter is almost like a yardstick, but in the metric system. So if it's 400 to 700 billionths of a meter, let's think about a centimeter as 100, a millimeter as 1,000. So it gets a lot smaller than a millimeter is what these wavelengths are going to look like. So those are the only ones we can see, from 400 to 700. And then there are other types that we can't see. So sort these different colors of visible light according to the wavelength and frequency. So I actually don't know what the answers are to these because there aren't any clues for me. So we're going to have to kind of guess and check together. So make a prediction. 650. What do you think? Which color do you think has a wavelength of 650? Let's check red. Oh, good job. Red light has the longest wavelength and the lowest frequency of the visual spectrum. Has the longest wavelength because it's spread out. So they count the tops and the distance between the tops. So it has the longest wavelength, and the frequency is how many there are. There's only two of them in this second. So you have to think about how many bumps there are and how far apart they are. All right, what's your prediction for 590? I'm going to go with orange. I'm kind of thinking maybe it's the rainbow. All right, correct. Orange light has a slightly shorter wavelength than a red light. Modern sodium street lights give off orangish light. So you notice that they're just a little closer together. And if I'm going by the rainbow, I'm going to go with yellow next. You got it. Incandescent bug lights are yellow because insects have a hard time seeing yellow lights, and they are therefore less attracted to light bulbs of that color. Bug lights. That's kind of interesting. All right, let's see. Roy G. Excellent. Green light is one of the primary colors of light, along with red and blue. When red, green, and blue lights are mixed or added together with the proper intensity, we see white light. I think that you guys worked on the primary colors in the color wheel with Mr. Van Bekoven this year. So you should be able to see that they're getting to be closer together, and there are more of these bumps on them. Let's see, Roy G. Biv, blue. Yes, because of its wavelength, blue light and sunlight is absorbed and scattered by gas molecules in Earth's atmosphere. Longer wavelengths, like red and orange, pass through unaffected. That's why the sky looks blue. Holy moly, we need to reread that. Because of its wavelength, blue light in the sun is absorbed and scattered by gas molecules in Earth's atmosphere. So in the sky, when the wavelengths from blue come from the sun, and when they hit our atmosphere, the gases make them scatter all over the place, which is what makes the sky blue. Longer wavelengths like red and orange pass through unaffected. That's why the sky looks blue. So the wavelengths for orange and red come through and they don't change. They don't scatter all over the sky. They just stay in one spot, which is why we can tell that the sun looks like red or orange or yellow. But blue gets scattered when it hits the atmosphere. That is incredibly cool. I'm really glad that we learned that. All right, and violet. That's right. Violet light has the shortest wavelength and the highest frequency in the visual spectrum. So remember that the wavelength is the difference between the bumps, and the frequency is how many bumps there are. Good job, guys. Congratulations. The visual spectrum is a small part of the electromagnetic spectrum. The visual spectrum is a small part of the electromagnetic spectrum. So from 400 to 700 is what our rainbow is. And then all these other waves are waves that we can't see. Across the electromagnetic spectrum, the higher the frequency of the wave, the shorter its wavelength it has, and the more energy it has. X-rays have more energy than ultraviolet rays. So here's X-rays. Notice that the wavelengths are much closer together. X-rays have more energy than ultraviolet rays. X-rays can travel not only through your clothes, but through your skin and muscles as well. However, ultraviolet lights are blocked by some fabrics. Ultraviolet's back here. So that would be light from the sun. So if you're wearing clothes, you're not really going to get much of a sunburn under your clothes because these kind of lights aren't strong enough to go through your clothes. But an X-ray is, which is why you don't have to take all your clothes off if you break a finger or something and have to go get an X-ray. Let's see. However, ultraviolet rays are blocked by some fabrics, and you can reduce your chances of getting a sunburn by simply wearing a shirt. All right, I think that's all of it.